What is going on, guys? My name is Amos and I'm back again with another series of videos. So in this series of videos, we'll be talking about numerical analysis. So what exactly is numerical analysis? Now, at its core, numerical analysis is about developing and analyzing algorithms that approximate mathematical problems. Now, whether it's solving equations, finding integrals, or understanding differential equations, numerical methods give us tools to approach these problems in ways that computers can handle much more efficiently. Now, what exactly must you guys expect from this series of videos? So first of all, start by building a foundation in the basic principles of numerical methods, error analysis, approximation, and then convergence. But then before all that good stuff, we have to first of all look at a few mathematical preliminaries. So these are things that I'm going to assume that you guys have already taken maybe some entry-level calculus course, and you've at least taken real analysis to be able to understand what is going to follow. Now, in this series of videos, I'm going to basically walk you through some of the most important results and some of the most important concepts that we are going to borrow from the previous courses that you guys have already taken, and we're going to use in this particular series of videos. So first of all, talk about sequences of real numbers, limits and continuity, differentiation, integration, and the most awesome Taylor's theorem, and then we'll also talk about orders of convergence. Now, see you guys in the next video, and let's get moving. What's going on, guys? My name is Amos and I'm back again with another video. So in this video, we're going to be talking about sequences of real numbers. Now, before we even start talking about sequences of real numbers, let's first of all define what a numerical sequence is. So a numerical sequence is going to be a mapping from some subset. So let's say we have some mapping. Now, let's say we're going to call it F, for example. So a numerical sequence is going to be a mapping from some set from some subset of the set of natural numbers, into some field F that we are calling F, right? And then what this is going to do is that it is going to associate to every natural number n some real number, some number a sub n, like so. So this is what the definition is saying. So this is what a numerical sequence is. Now here we're talking about real valued sequence. Now what this F represents here is this F can either be the complex numbers or the real numbers. Now since we're talking about sequences of real numbers, this F here is going to be equal to the set of real numbers. So this is just a real number here, and then this is just some natural number in the set n1, which is going to be a subset of the set of natural numbers. Now in terms of notation here, a sub n here is just any real number. But then if we add the curly braces here, then this is going to become a sequence. So this is what the definition here is saying. Now let's first of all talk about stationary sequences before we go any further. Right, stationary sequences are going to be sequences that are going to be constant, or that are going to have the same term, that are going to have the same real number. Let's say a sub k, starting from a certain range. So let's say we have examples of stationary sequences. So here, let's say stationary sequences, and then we can talk about, we can write a few examples of stationary sequences. Now the sequence, for example, 1, 1, 1, 1, 1, 1, and then we have the ones continue. So this is a stationary sequence because we can see that all the terms, all the numbers are the same here. So we basically have a 1. Now this is a stationary sequence starting from the very first term. Now this is going to be a0, and then this is going to be a1. Now this is going to be a2, and then this is going to be a3, and then we have the other terms there. Now we can also have a sequence like this one, for example. Let's say we have 2, 3, 4, maybe 5, and then we have 1, 1, 1, 1. Now this is also a constant sequence, but then starting from this term here, So this is, if this is your a0, and then this is your a1, and then this is going to be your a2, and then this is going to be your a3. Then starting from a4, we can see that all the numbers are the same. So this is basically going to be another constant sequence. So the sequence doesn't have to be constant starting from the very first term. It has to be constant starting from some term. If we have the same number starting from some term, which is not necessarily the first term, then the sequence is going to be a constant sequence. We also have sequences that are going to be sequences of positive numbers, sequences of real numbers that have positive numbers. So we're going to say that we're going to have a sequence of positive numbers. So let's define a sequence of positive numbers So we're going to have a sequence of positive numbers if for all values of n in the set n1, which is going to be a subset of the set of natural numbers, if for all values n in the set n1, which is a subset of the set of natural numbers, if we have that, every real number s sub n that is going to be mapped to this n that we have here, if every such real number is going to be greater than or equal to 0, then this is going to be a sequence of positive numbers. So this is going to be a sequence of positive numbers. Now, similarly, we can now define a sequence of negative numbers. So we can have what is known as a sequence of negative numbers. So we can also have what is known as a sequence of negative numbers. So negative numbers, like so. Now, this is basically the other way around. So if for all values n in n1, which is going to be a subset of the set of natural numbers, if we have that every real number that is going to be mapped to every n here, if every real number is less than or equal to 0, then this is going to be a sequence of negative numbers. Now let's talk about the equality of two sequences. So when are two sequences equal? When can we say that two sequences, s sub n and b sub n are going to be equal? So here is the definition. So let's say equal sequences, and then for reference, then maybe we can, do something like this. So equal sequences. So we say that the two sequences a sub n and b sub n are equal. So if are going to be equal if for all values n in the set n1, which is going to be a subset of the set of natural numbers, if for every n we have that, a sub n is equal to b sub n. If this is going to be true for all values of n in this set n1, which is going to be an infinite subset of the set of natural numbers, then the two sequences are going to be equal, right? Now let's talk about different ways of representing sequences. Now, there are many ways of representing sequences. So here, let's talk about representation. So how do we represent sequences? Now, the first, approach is going to be, you'll be given, a general term for some sequence. Now, they'll say, let's say, maybe s sub n is going to be equal to 1 divided by n. Now, this is going to be for some n in the set. So n star, we basically have to exclude 0 because we are basically performing some division here, and we know that division by 0 is going to be criminal. So every term of our sequence is going to be given by the general term 1 divided by n. Now this is one way of defining a sequence. Now this is what is known as the explicit definition of a sequence, where you are given the general term. Now another representation is you'll be given, maybe let's say some u0 is equal to some starting number. Maybe let's just say 2 as an example. And then what will follow is going to be some recurrence relation that is going to help you find, subsequent terms of the sequence. So for example, then they'll give you this recurrence relation, un plus 1 is equal to maybe let's say 1 divided by 2 plus maybe 3 un. They'll give you some recurrence relation. And then since you have this and you have this recurrent relation, then you can find the subsequent terms of the sequence. Now, this is known as a recurrence relation. And then this is going to be the starting term, right? So this is going to be the starting term. Now, of course, there are many things that we cannot talk about, but for the purpose of this video, these few details or these few pieces of information are going to basically do justice to, basically going to do justice. Now, let's look at the graphical representation of let's first of all maybe define the limit of a sequence. What is a limit to some sequence? What is the limit of a sequence? So we have this very long definition. Now I'm going to make sure that I sort of like explain this very long and scary definition to you in a very simple manner, right? Now the first part here is saying, so we call x the limit of the sequence x sub n. Now remember that the notation we've adopted here is we want to use the curly braces here, but this is basically the same thing, right? So we call x the limit of the sequence x sub n, which is written, x the sequence xn is going to go to some number x as n goes to infinity, or the limit as n goes to infinity of the sequence x sub n is going to be equal to x, then this is the formal definition, right? So this is going to be the case if for each real number epsilon, so for some positive real number epsilon, which is usually taken as a very, very small number, right? Which is a very, very small number. Now, there exists a natural number n, and if we attempt to go beyond this n, then all the terms of my sequence are going to be in the region, as we are going to see, x plus epsilon, x minus epsilon. So basically here, what we have here is that the sequence is basically going to approximate the real number x to within epsilon. So this is what we have here. And then this is the mathematical statement here. Now, this is, just me using, the English language. But then this is the mathematical definition that is very, very concise, and it basically means whatever is written here on top here. So for some positive number epsilon, we can find some natural number in the set. We can find some natural number, and then if we go beyond this natural number n, then the sequence x sub n is basically going to approximate this real number x. Okay, now this real number is the limit of the sequence to within epsilon. And then if such a number exists, then we're going to say that the sequence is going to be convergent. Otherwise, the sequence is going to be divergent, right? And then let's look at the diagram here and basically see what is happening here. So look, all the dots that we have here, let's first of all talk about, let's first of all look at this diagram, and then we can now move to the first one. Now, if you look at the first diagram here, let's examine what we have here. Now, all the dots here represent the terms of my sequence. All the dots here represent the terms of my sequence. Now, we can see here that starting from this point here, maybe what we can do is this. Starting from, now that's not very precise. Now, starting from this point here, now we can see that all the terms of my sequence are in the region a plus epsilon, a minus epsilon. Now remember here, in the definition we have x sub n, but then what we can do is that we can give ourselves some a sub n and then minus a. Then it's basically going to be the same thing. Now, if you look at this expression here, now let's first of all try to develop this particular expression. So what if you get rid of the absolute values, then you have minus epsilon, and then less than a sub n minus a, and then less than epsilon. Now what we're going to do is that we're going to add a throughout, and then we're going to have a minus epsilon less than a sub n, and then we're going to have a plus epsilon. So we can see that all the terms of my sequence, are going to be in the region, like all the dots are going to be in the region a plus epsilon, a minus epsilon. So if we go beyond this n, so for some n taken for some n that is large enough, we see that all the terms of the sequence are in the region a plus epsilon, a minus epsilon. Now, in general, if you choose a smaller value for epsilon, if we choose a small value for epsilon, then this n is going to get bigger. So as we can see here, we see that here we have some n0. Beyond this n0, we see that all the terms of the sequence are in the region. If we go beyond this n0 here, what we notice is that all the terms are going to be in the region. Maybe let's say this is going to be in the region a plus epsilon, a minus epsilon. So this is going to be a plus epsilon, and then this is going to be a minus epsilon. But then if we choose a smaller value for epsilon, which is epsilon 1 here, now we see that now our n, we need to choose a larger value for n. Now in this case we have some n1. Now if we go beyond this n1, we observe that all the terms of my sequence are in the region a plus epsilon 1, a minus epsilon 1. So that's all there is here. So to summarize, what we're saying here is the sequence here, if we, for some n large enough, so as n goes to infinity, what we observe here is that the sequence a sub n is going to approximate its limit, which is a, to within epsilon. So to within epsilon. Now this approximation can be made, as accurate as we want, or as accurate as possible, by taking a very big value for n, which is going to imply that we need to choose a smaller value for epsilon, and then the approximation can be refined in that particular way. Now, thank you guys for watching, and I'll see you in the next video where we'll be talking about other things about sequences. Thank you guys. Guys, it's Amos here, and I'm back again with another video. So in today's video, we want to talk about the limit laws. But before we start, let me first of all clarify, let me just first of all talk about a few things to continue from, where we left the previous video. Now, let me first of all explain, make mention of the fact that if the limit exists, then the limit is going to be unique. So this is very, very important in the sense that convergence is going to be well defined. If we have, multiple limits, then it would mean that the sequence is going to converge to multiple numbers simultaneously, which is going to be very, very cumbersome and very, very ambiguous. And then most concepts such as differentiation rely on the fact that the limit of a sequence is basically going to be unique. Now, of course, I'm not going to give you a formal proof. Maybe I'm not going to show that the limit of a sequence, if we can find some number or some real number that is a limit to some sequence, then that number is going to be unique. So we're not going to do that in this video, but it's just something that is that you must remember, and something that is very, very important, especially that we'll be talking about differentiation and other related concepts later on. And then the sequence doesn't have to be defined starting from the very first step. For example, we said that a numerical sequence is basically a mapping from some set n1, which is a subset of the set of natural numbers, to some field f. Now, in our case, f is going to be equal to the set of real numbers. Now, if you look at the sequence un, now we talked about representation of sequences. Now let's simplify things, and let's look at this sequence here, root of n minus 4. If we are to talk about real valued sequences, then we must make sure that whatever is under this root, or whatever is under this square root, we must make sure that it is greater than or equal to 0. So what value of n, starting from what value of n is this sequence going to be well defined? Well, starting from 4. So 4, so this sequence is defined for n greater than or equal to 4. Now, anything that is less than that, we're going to get a negative number, and then the sequence is not going to be well defined. And so if we are to talk about a real sequence here, a real valued sequence, or a sequence that has real numbers, then whatever is under the square root has to be, in this particular case, greater than or equal to 4. All right, let's now look at the limit laws. All right, so let's say we give ourselves two sequences, a sub n and b sub n. And then we make the assumption that the limit of the sequence a sub n exists, and the limit of the sequence b sub n exists. And then what would be the limit of the sum of the two sequences? So here we're saying that the limit of the sum of the two sequences is basically the limit is the sum of the limit of the individual sequences. So here we have the limit as n goes to infinity of a sub n plus the limit as n goes to infinity of b sub n. Now, this is known as the sum law. Now, what follows here, we can also have the difference law, but then here, what follows here is the constant multiple law, like so. So if we multiply the limit as n goes to infinity of this item that we have here, c, some constant number c, some constant real number c, multiplied by the sequence s sub n, or multiplied by some term of the sequence s sub n. Now this is going to be our sequence here. So some real number c multiplied by our sequence s sub n, or the limit of this quantity that is on the left is basically going to be this same constant multiplied by the limit as n goes to infinity of our sequence s sub n. Now this is going to be true for any real number c that we have here. And then we have the product law. We have the product law now, which means the product, the limit of the product of two sequences is basically going to be the product of the limits of the individual sequences. So here we have the limit of the sequence a sub n as n goes to infinity, and the limit as n goes to infinity of the sequence b sub n. Then we also have what is known as the quotient law. And as we all expect, this item here has to be different from 0, because we're dividing by, we are performing some form of division here. And then if if the denominator is 0 and our numerator is a constant number here, which is 1, then we're going to have a problem. So for this quotient law to be defined, we must, it is a must that all the terms of our sequence are different from 0. Thank you guys for watching, and I'll see you in the next video. What is going on, guys? My name is Amos and I'm back again with another video. So in today's video, we want to talk about bounded sequences. So let's talk about first of all a sequence that is bounded above. So we say that the sequence a sub n is going to be bounded above if we can find a real number big M such that all the terms of my sequence are going to be less than or equal to this real number big M and big M. All right, so this has to be true for all values of small n in the set of natural numbers. Then our sequence is going to be bounded below if we can find some real number small m such that all the terms of my sequence are going to be greater than or equal to this small m. Now this has to be true for all values of n in the set of natural numbers. So a sequence that is bounded above and bounded below is going to be bounded. It's going to be a bounded sequence. So we say that a sequence is bounded if it is bounded above and bounded below. Now let's look at a few examples of sequences that are bounded above. So let me give you an example of a sequence that is bounded above. So the sequence a sub n is equal to sine of n. Now this is for n, for some natural number n. Well, this sequence is bounded above. So this sequence is bounded above. This sequence is bounded above. Now this is because, so this is my justification. Then we know that the absolute value of our a sub n, which is equal to the absolute value of sine of n, like so, is always going to be less than or equal to 1. Now if you take sine of anything, now we also know in principle, what we have is that sine of anything is going to be between 1 and minus 1. So this is what we basically have. So this is an example of a bounded sequence, or a sequence that is bounded above. So we can say that our sequence is bounded above by 1 and then bounded below by minus 1. So our sequence is bounded. Now, example number 2, let's look at the sequence b sub n, which is going to be equal to e to the power n. Now this sequence is going to be unbounded. Now this is going to be unbounded because if we say if for all values m in the set of real numbers, if we choose small n is equal to the flow of natural log of, for example, n plus 1 plus 1, like so, then what we have is that the sequence, my sequence, which is b sub n, well, what we have here is that our sequence b sub n is going to be strictly bigger than this m. So we see that our sequence here is not going to be bounded above, right? So we're going to have a problem. So if the sequence is not bounded above, then it cannot be bounded, and so this is why I'm saying that our sequence here is unbounded. So we can actually check that this is actually the case. So what we have here is the flow function. So we basically take the integer part of our, we take the flow of our real number. Now this n here has to be a natural number, and so if I leave it the way it is, like so, then there will be a problem because n has to be a natural number. And so that is why here I'm taking the flow of this real number here. So we have to take the flow of this function here. Now another example of a function that is not bounded another example of a sequence that is not bounded is the following. So the sequence un, which is equal to n, like so, is not bounded. So this sequence is not bounded. Now it's very easy to verify or to see that this sequence is actually not bounded. Now let's look at one very, very important theorem when it comes to bounded sequences. So we see that every convergent sequence is going to be bounded. So every convergent sequence is bounded. Now the reverse, or the reverse is false in general. Now the reverse is false. So let me just maybe do this. So what we are saying here is that the reverse is actually false. Now we can give a counter example here. Now consider the sequence. So let's consider the sequence. Let's consider the sequence C sub n, which is equal to -1 to the power n. Now what are the terms of this sequence? Well, the terms of this sequence are as follows. So we basically have, if you plug in the first item, now here n is going to come from the set of natural numbers. So if you plug in your 0, you get 1. So the first item is 1, the next number is -1, and then the next item is 1, and then we have -1, and then the numbers keep on alternating. The numbers keep on alternating. Now you see that this sequence does not settle down to a single value. Now because it is sometimes 1 and then sometimes -1, so this sequence C sub n is not convergent. So C sub n is divergent, right? So C sub n is a divergent sequence. So we know that C sub n is going to be a divergent sequence, right? So it's a divergent sequence, but then this sequence is bounded because all the values are, so we have 1 and -1. So the biggest value we have here is 1, and then the smallest value here we have is 1. Cn is divergent but bounded. Okay. Because it's bounded. Why is it bounded? So maybe we can give some proper justification here in curly braces. So here we have that -1 to the power n is less than or equal to 1, and then less than or equal to -1, like so. So we see that our sequence here is bounded. So however, we have a bounded sequence, but then this sequence is also divergent. So that's why here we're saying that the opposite is always false. That the opposite is in general going to be false. Now there are sequences that are bounded and that can also be convergent, but then in general the opposite is always going to be false. Now another interesting thing about this bounded sequences, or something that is going to be mentioned in line with these bounded sequences, is the fact that every sequence, let me just maybe write it here. So every sequence that diverges to positive infinity, every sequence that diverges to positive infinity is bounded below. Then every sequence that diverges to minus infinity is bounded above. That diverges to positive infinity is bounded above. Now let me just define what it means for the limit of a sequence. So here what I'm saying is that every sequence that has limit positive infinity is bounded below, and then every sequence that has limit minus infinity is bounded above. Now let me define, or let me first of all write what it means for a sequence to have limit positive infinity and a sequence to have limit minus infinity. So we say that the limit, as now let me just put this as a reminder, like so. We say that the limit as n goes to infinity of some sequence, S sub n, is going to be equal to positive infinity. Well, this is going to be equivalent to saying that for all values big M in the set R plus star, like so, we have that we can find some natural number n in this. We can find some natural number n, like so. We can find some natural number n such that for all values of n in the set of natural numbers. So just going to write it on on the next line. So if we go beyond this natural number, then we have that our sequence un is going to be greater than or equal to m. And then recall that the limit as n goes to as n goes to infinity, of our sequence a sub n is going to be equal to minus infinity. Well, this is going to be equivalent to saying that we can find some m that is going to be in the set r minus star, like so, and then we can find some natural number such that for all values small n in the set of natural numbers, if we go beyond this n, then this is going to imply that that my sequence, this is going to imply, now here I must have, instead of having u sub n, I must have a sub n for everything to make sense. And then maybe here we can use a different sequence. Instead of having, a sub n, we can maybe use b sub n. Then here we can say b sub n is going to be less than or equal to m. Now this is just me reminding you what it means for a sequence to have limit positive infinity and for a sequence to have limit minus infinity. Thank you guys for watching, and I'll see you in the next video. What's going on, guys? My name is Amos and I'm back again with another video. So in this video, let's talk about monotone sequences. Now let's look at the definition. So let's give ourselves some sequence x sub n. So we say let x sub n be a sequence of real numbers. So we say that the sequence x sub n is going to be increasing if it satisfies the following inequalities. So what we basically see here is that we see that x1 here is our first term. Now our first term can even be x0, but here we start at x1. So we said our first term is x1, then our second term is x2, and then we have the other terms that follow. Now we see that the previous term is always going to be, if the previous term is always less than or equal to the next term, then if that is true for all values of n, now this has to be true for all values of n in the set of natural numbers, then our sequence is going to be increasing. Then decreasing is the other way around. So if you look at all the terms of our sequence, we see that the previous term is always going to be bigger than the next term. Now, if this is true for all values of n in the set of natural numbers, then our sequence is going to be decreasing. Now, a sequence is going to be monotone if it is either increasing or decreasing. Now, if we change the sign here, instead of using the less than or equal to sign, if we use the strictly less than sign, then here we're going to have a strictly monotone, a strictly increasing sequence. Then if we use a greater than, a strictly greater than, instead of using a greater than or equal to, then we're going to have a strictly decreasing sequence, right? So this is what a monotone sequence is. So a monotone sequence is a sequence that is either increasing or decreasing. Now let's look at some examples of monotone sequences. So examples of monotonically increasing sequences. So examples, let's look at some examples of increasing sequences. Now the first example that we are going to look at here is we'll take a very simple example. Now let's look at x sub n, which is given by the terms 1, 2, 3, and then maybe we continue. Okay, we continue like so. And then if these numbers keep on increasing, maybe 4, 5, 6, 7, 8, 9, if we keep on going, so this sequence is going to be an increasing sequence, right? This sequence is going to be an increasing sequence. Maybe to help you understand what is happening here is I'm just going to put n here, but then we can have an infinite sequence. Okay, so here n is coming from the set of natural numbers. So we see that this sequence is clearly an increasing sequence. Then example number 2 is the following sequence. So the sequence, maybe let's use maybe a different color and maybe a different name. So if we choose maybe y sub n, which is the sequence, a, and then a squared, and then a to the power 3, and then maybe we keep on going like so. So we have to be very careful here. A has to be strictly greater than 1, because if a is equal to 1, then we're going to have a stationary sequence because we're going to have ones throughout. So this is also another monotonically increasing sequence. So this is an increasing sequence. Then let's look at examples of decreasing sequences. Examples of decreasing sequences. So let's look at examples of decreasing sequences. Now I'll give you guys a very, very simple example, similar to example number 2. We'll actually start with that particular example. similar to example number 2, or the sequence b squared, and then b to the power 3, and then if we keep on, maybe we have b to the power n here, and then we keep on going like so. And then if b is between strictly between 0 and 1, well, then this is going to be a decreasing sequence. So you have to be very, very careful here. And then another example of a decreasing sequence is the sequence, maybe here we have 1, and then 1 divided by 2, and then 1 divided by 3, and then maybe we have 1 divided by n here, and then maybe we keep on going like so. So this is an example, this is another example of a decreasing sequence. Now, whenever it comes to talking about monotone sequences, we always want to talk about the monotone convergence theorem. So very, very important theorem. So we see that for a non-decreasing for a non-decreasing and bounded above sequence of real numbers. So what we're saying here is a non-decreasing sequence is basically we are in the first situation here. We are in the first situation. We are in this first situation. So this sequence is non-decreasing. So we are basically in this first situation. But maybe we might change the sign here to a less than. All right. So we're in to simplify things, we are just in this first situation here. So for this type of sequence, we see that the limit is going to exist. The limit is going to exist, but then the limit is going to be the supremum. So another way of writing this is, so maybe just to eliminate some of the noise that is here, what we can say here is that the limit of a sequence that is monotonically increasing, okay, the limit of a sequence that is monotonically increasing. So here we've used a sub n. Well, this is equivalent to this. So the limit of the sequence a sub n. So maybe here we can say, a sub n, the limit of the sequence a sub n is going to be equal to the supremum, of, so here we have of the terms a sub n, so such that, n is going to be a natural number. And then, so maybe here we need to use the curly braces like so. And then same here, we are in the second situation, right? We're putting ourselves in the second situation. So we're basically in this situation. So let's just make reference to what we've written here. So we are basically in this second situation, right? For a non-increasing and bounded below sequence of real numbers, well, this is what we basically have. So to maybe come up with something that is similar to what we have here, what we are saying here is that this is equivalent to saying that the limit of the sequence a sub n, like so, in this particular case, if we are in this situation, second scenario, then it is going to be equal to the infimum of the sequence, a sub n. Now, a sub n here is this one. This a sub n here is a real number, and then when we put the curly braces here, we're talking about the sequence, and then this has to be true for all natural numbers and for all natural numbers here. And so that is all about monotone sequences and the monotone convergence theorem. I'll see you guys in the next video where we'll be talking about other interesting things. We've covered a lot so far, and I hope to see you guys in the next video. What's going on, guys? My name is Amos, and I'm back again with another video. So in today's video, we want to talk about sub sequences. So whenever we have some infinite sequence, let's say a sub n in this particular case, so we have some infinite sequence, a sub n, and then if we decide to sort of like drop some terms of a sub n, and then maybe get and leave out some terms of this sequence a sub n, we see that we generate another infinite sequence. In this case, we call that infinite sequence b sub n. Then this sequence b sub n that is going to be extracted from the existing a sub n sequence is basically going to be a subsequence of this sequence a sub n. So another important thing to note here is that the sequence a sub n is basically going to be an infinite sequence, and then the sequence that is going to be extracted from a sub n is also another infinite sequence. So we can take some example here. We can look at some example here. So let's say we have the sequence, a sub n that is basically equal to 1 divided by n. So let's say we have a sub n is equal to 1 divided by n. Then maybe let's write out a few terms of this sequence. So the first term is 1 divided by 1. And then here, let's specify that n is coming from n star. And then we have 1 divided by 2. and then we have 1 divided by 3, and then we have 1 divided by 4, and then 1 divided by 5, and then we can go on, and maybe 1 divided by k, like so, and then the terms, keep on going, because this is an infinite sequence. Then if we extract this sequence here, a to n, now here there's one thing that we are supposed to observe, one thing that we're supposed to respect about this function that we have here. So here we have a function of n, f of n is equal to 2n. Now this function, according to this definition that we have here, this function has to be a mapping from the set of natural numbers into the set of natural numbers. So here, let me write it here. We see that f has to be a mapping from the set of natural numbers into the set of natural numbers. And then this function, or this mapping, has to be strictly increasing. So meaning we must have n's such that n1 is strictly less than n2, which is strictly less than n3, and then which is strictly less than n4. And now because our function is strictly increasing, what is going to happen is that if I compose this and sort of like take my function here, I'm going to have this basic situation. So all in all, we must have n's such that we have n1 is less than n2, less than n3, and then the numbers keep on going like so. So if we extract this sequence a to n, now 2n here is going to this sequence is going to contain the even term, is going to have even values of n. We'll be basically using the even terms, right? So here we're going to have 1 divided by 2, which is going to be our first term, and then we'll have 1 divided by 4, and then we'll also have 1 divided by 6, then we'll also have 1 divided by 8, and then we have 1 divided by 2k, and then the terms are going to continue. So if you look at this value, this is my n1, this is my n1 here, this 2 that we have here is my n1. So if we look at this number here, this is my n2, we see that n1 is going to be less than n2. Now same thing here, this is going to be my n3. Let me just circle it like so, and then we observe the same pattern here. And then we can also extract another sequence. We can also extract another useful sequence, which is the sequence a to n plus 1, like so. Now, which is going to contain the odd values of n. So here we're going to have 1 divided by n, 1 divided by 3, 1 divided by 5, and then we have 1 divided by 2k plus 1, 1 divided by 2k plus 1, 2k plus 1, and then the numbers keep on going. So we see that this is also an infinite sequence, and then this is also an infinite sequence. So this is our b sub n, and then this is maybe our c sub n, if you want to basically follow what is happening here. And then a sequence like this one is not a subsequences. So examples of sequences that are not subsequences of 1 divided by n. So let's look at this sequence here. Let's look at this sequence. Maybe let's call it d sub n. And then we have a sequence like this one, 1 divided by 2, and then 1 divided by 1, and then 1 divided by 4, and then 1 divided by 3, and then if we keep on going like so, then this sequence is not going to be, this one is not a subsequence. So this one is not a subsequence. Not a subsequence. Not a subsequence of the sequence 1 divided by n. So this is very clear to understand, that this is not going to be a subsequence. Right. So we can have many examples of sequences that are not subsequences, but then we basically want to leave it here. And then one very interesting thing about sequences and the subsequences is the fact that if the sequence a sub n converges to some limit a, then all the subsequences of the sequence a sub n are going to converge to the same limit, which is a, right? So very important piece of information. And in fact, we can use subsequences to check if a particular sequence is going to be convergent or not. So if we can find two subsequences of some sequence a sub n, and if those two subsequences converge to different limits, then the sequence is not going to be a convergent sequence. Now let's give ourselves some example. Now let's give ourselves some example of this of a particular situation. Let's say we have some sequence b sub n, which is equal to -1 to the power n, and then now two subsequences of this sequence. So we have the sequence b to n, and which is going to have 1. So 1, 1, 1, 1. So if you plug in any, even number here for n, you basically get 1s, and then this sequence continues. And then this goes to 1, this goes to 1 as n goes to infinity. And then we can extract another subsequence, which is b to n plus 1, which is going to have minus 1, minus 1, and then minus 1, and then minus 1, and then all the other terms. So this is going to go to minus 1 as n goes to positive infinity. So we see that this sequence is not going to be convergent. This sequence, we know that this sequence is not convergent, but then here we want to use the subsequences. So we found two subsequences of the sequence b sub n that converge to different limits. And so this one is not convergent, right? Because if a sequence is convergent, then all these subsequences have to converge to the same limit as the given sequence, in this case, which is a sub n. So here it does not work. And then another interesting theorem on subsequences is the Bolzano-Weierstrass theorem, which tells us that from every bounded sequence, we can basically extract a convergent subsequence. So if we have a bounded sequence a sub n, we can extract at least one convergent sequence, which is going to be a sub nk. Thank you guys for watching, and I'll see you in the next video. What's going on, guys? My name is Amos, and I'm back again with another video. So in today's video, we want to talk about Cauchy sequences. So let's say we have a sequence x sub n, which is an infinite sequence. Now this sequence is going to be said to be Cauchy when we fix some value epsilon that is strictly positive, then we can find some natural number m such that the terms of the sequence, any two terms of the sequence beyond, if we attempt to go beyond this m, any two terms of the sequence are going to be, the distance between those two terms is going to be very small, meaning the terms are going to be very close, and then the distance is basically going to be less than this value that we have here, epsilon. Maybe let's write it in another way. Let's maybe write one very long mathematical definition or a mathematical statement. So what we're saying here is for some epsilon, for some value epsilon that is strictly positive, if we can find some natural number m, and then for all values n in the set of natural numbers, we basically want to sort of like get any two terms of our sequence. And then if we basically try to observe what is happening beyond this particular m, if we try to observe what is happening beyond this particular m, then we see that the distance between these the two terms of the sequence is going to be very small, and then the distance is going to be smaller than epsilon. The distance is going to be smaller than epsilon, because what the absolute value is going to do is that it is basically going to measure the distance between the two terms of the sequence. So here we have x sub n, and then maybe we can say x sub m. Now you can basically keep the k here, but then it's the same thing, right? It's the same thing. We've only changed the letter we are working with. So this is what a Cauchy sequence is going to be. And then we can look at some maybe illustration here. So you can play around with this diagram, maybe try to fix some value for epsilon, maybe fix epsilon, maybe 0.5. Let's take 0.5 for epsilon. Take 0.5 for epsilon. And then we can see that starting from maybe this point here, if you basically grab any two terms, if you grab any two terms of your sequence, we see that the distance between those two terms is going to be less than epsilon, right? So that's all I had for you guys for Cauchy sequences, and I'll see you in the next video.